impressive city, Hong Kong, and now I have to come to a smaller scale. It's quite a different scale in Germany and in Berlin, and especially in Hohenneundorf, the city I have to talk about now. My name is Ingo Lutkemeyer. I'm the head of a small architectural office with which offices in Berlin and Bremen, which is in the north of Germany. I was asked to give some thoughts about innovations at school, and I will show you the first plus energy school building that is realized in Germany. Based on the ambition of the city of Hohenneundorf, which is a small city north of Berlin, to become a green city, and the need to minimize the long-term running costs, the main objective for the design was to develop a sustainable concept that provides good learning and teaching conditions with low operational costs for the commune. Therefore, an interdisciplinary team has been formed. You see all the names on this list, and I show you this because I think it's important to mention that not only architects are doing the design for those projects, but a big group of experts on the different fields for the design. Hohenneundorf is a small town north of Berlin, in northern Germany, on the latitude of 52.7 degrees north. This is quite different to Hong Kong. I think Hong Kong is 25 degrees north, 22.4, okay? So the climate is quite different here and to the climate in north of Germany. So what I can present today is not the solutions, but maybe it's some kind of a design strategy, some ideas that are right in the north of Germany, and maybe there are some things we can transfer to this area. The neighborhood in Hohenneundorf is characterized by low-rise residential buildings, sport facilities, and it's a typical suburban area in Germany. The project comprises of the construction of a primary school with an integrated sports hall. The idea of the project was to realize an integrated design approach that conceives all technical, low energy and functional requirements as an integral part of the architecture and permits a lean technical concept with a simple, easily controllable and low maintenance engineering system for reaching a high comfort indoor climate. The design should provide excellent learning conditions regarding spatial quality, air quality, thermal and visual comfort. The primary school is designed for 540 pupils in 18 classrooms. A central school avenue connects the two entrances with all functions of the building. Administration and teachers' rooms are located near the entrance. The classrooms are grouped in 3 wings and are oriented to the south. Specialist rooms for arts, music, computing, nature sciences, and a small library are next to the entrance. A cafeteria is oriented to the east, and the sports hall is in the north. The first floor is organized in the same way. Classrooms facing south, specialist rooms at the school avenue, and the service room for the sports in the north. So a very simple organization for the floor plan. So I can come to the sustainable building and energy plus concept. The main features of the sustainable building and energy concepts are a highly insulated passive house standard, a new hybrid ventilation concept, an optimized behavior conditions, optimized daylighting performance, the use of renewable energy sources, and the integration of innovative building components. Let us first look at the building construction details. The main structure of the building comprises of concrete walls, concrete ceilings, and a concrete roof for the school building, and the timber roof construction for the sports hall. The building has a very good thermal insulation level that achieves the passive house standard values you can see of 0.15, very good values in the triple glazing for the windows. In cooperation with the teaching team, a room concept has been developed that enables transparency and flexibility for the teaching of the young children. The heart of this concept is a teaching unit for one class, which is more than a simple classroom. The teaching unit, called home area, consists of a multifunctional room in combination with a smaller teaching room, an extended circulation space, a wardrobe, and a sanitary unit for each class. So each class has this room configuration. This concept enables different kinds of teaching situations and is also strongly related to the technical concept for ventilation and lighting. The hybrid by grouping the classroom and sanitary unit to a so-called home area, a combination of natural and controlled ventilation could be realized. The natural ventilation is done by opening the windows, and the mechanical ventilation by using a simple ventilation system. The advantages of both ventilation types are combined to a hybrid ventilation strategy to create a good balance of thermal comfort, air quality, user acceptance, and energy efficiency. The ventilation of the classrooms is primarily achieved by rapid natural ventilation during the breaks by using motor-controlled full-height vent windows. The windows open automatically during the breaks between the lessons and can also be used for night ventilation in summer. Additional windows for manual operations are available to enable individual control. The hybrid, with only natural ventilation, the CO2 levels in the classrooms would increase quickly during the lessons. Thus, the natural ventilation is combined with a small mechanical ventilation system to reduce the increase of the CO2 levels when the windows are closed. Supply air is given to the classroom, the exhaust air is taken from the sanitary rooms. The supply air flow for the classrooms correlates to the amount of the exhaust airflow needed for the sanitary units. This is a picture of the first measurements results that were done for the schools. You look at the gray curve, and this is the CO2 concentration in the classrooms, and you can see here the effectivity of the opening of the natural ventilation of the opening for the windows. You can see the very good how the CO2 concentration goes down. As I mentioned before, the strategy for thermal behavior is based on the use of the thermal mass. Therefore, the concrete ceiling could not be covered by sound-absorbing materials. One research object in this project was the trade-off between thermal storage and the concrete ceilings on one side and a good room acoustic quality on the other side. To achieve best possible results for both requirements, the concrete ceilings are left uncovered for good thermal contact, and the biggest part of the available wall surfaces is covered by highly efficient broadband acoustic absorbers. The reverberation time was measured and the results were pretty good. A high room acoustic quality, according to the ambition German standards, could be achieved without affecting the passive cooling function of the ceilings. Another important strategy is the use of daylight to reduce electrical energy demand for lighting, but also to provide attractive room atmosphere. The deep spaces of the classrooms receive natural light from two opposite sides, while the small room gets natural light from one single side only. Here you see the picture of a classroom, and you can see the big transparency and the access to daylight on both sides. Almost every space is designed to have a very high daylight autonomy. The circulation spaces are well oriented to the daylight to provide attractive room quality. The picture shows the central school avenue with the access to the schoolyard. The use of bright colors support the attractive appearance. Here, the two entrances to the sports and to the school. Not only the school avenue, but also all corridors of the classroom wings are well daylit, as you can see in this picture. The corridors provide space, transparency, and natural light for the children. The south-oriented facades of the classrooms have been developed carefully to provide efficient solar shading, natural lighting, and passive solar energy gains. Fixed exterior blinds protect the window against incident solar radiation in summer. Vertical fabric blinds enable efficient solar control due to users' requirements. The windows above the fixed blinds have a non-UV glazing to diffuse daylight, and the windows in the ground floor above the fixed blinds are equipped by external shading devices that are integrated in between the two layers of glass. Here you can see the appearance of the facade. The facade provides a shady atmosphere in summer, and the air circulation is possible behind the screens. Also, there's a good view to the outside when the shading is closed. Here you can see the light guiding louvers with the integrated solar protection. So when there's an incident, if there's a high solar status, then there's a good shading. And if the solar is not so high, the light is redirected to the ceiling. A view from the courtyard and another view with closed shading. And you can see here how you can see the shady atmosphere at the facade, and but the facade is slightly open, so it's not a closed facade. When the sun is shining, it's open to look outside. At the east facade of the assembly hall, we tried something different. We tried to realize electrochromatic glazing. This is a switchable glazing with two status, with different status for solar protection. The values are between 10% and 32% for solar heat gain. So it's a solar control glazing which is switchable. You can see it on the left picture. Some of the windows are a bit more blue and some others are a bit white. So this is the appearance. And a view from the inside of the assembly hall. The sports hall, there we did the daylight calculations to realize a good daylight distribution in this large room. The energy concept bases on the use of renewable energies. And these are two energies. One is the photovoltaic from the PV power plant, and the second is the wooden pellets we use for the central heating, and we also use for a combined heating power machine, a micro CHP that gives us 1 kilowatt on electrical energy and 5 kilowatts thermal energy. All these measures lead to a very low energy demand of the building. The calculated annual primary energy demand for heating, hot water, ventilation, cooling, and lighting is 23 kilowatt hours per square meter and year. We discussed 1 hour ago around 300 to 1,000 kilowatt hours per square meter and year. This is 23, so it's a very, very low value, and this is primary energy. The partial compensation of this need is realized by a micro CHP, which is used throughout the year to cover the basic loads for the compensation of the remaining primary energy demand. A building integrated photovoltaic solar power plant of 55 kilowatt peak is used. The annual primary energy production is 24 kilowatt hours per square meter and year. So it's 1 plus, but 1 plus is plus. So we did some calculations on the life cycle costs of the building, and this is, I think, quite an important aspect. The life cycle comparison was done for a German standard new building of the same size and shape according to the German standards 2009. It's so-called reference building, and it's also done for the new school. Here you see the investment costs and the costs, the accumulated costs over 50 years for the reference building, the construction, the operation, the cleaning, the maintenance, and the refurbishment. And this is a chart for the Plus Energy School in Hohenneundorf. You can see there's a bit more cost for the construction, but there's a big difference in the operation. This is 66% less operation cost during 50 years, and totally the life cycle cost of the building, including construction and operation, is 21% less than the reference building. So this means this building is over a 50 years period 20% cheaper than the reference building, and this, I think, is good news. If you look at the ecological quality, we can do this as well. The first thing is the primary energy that is used for the construction and for the operation of the building over 50 years, and we only look at this. The primary energy used, including the embodied energy, is 57% less for the school building according to a reference building, and this more or less the same. You can see if you look at the ecological parameters like global warming potential, ozone depletion potential, and so on. The blue columns is for the Plus Energy School and the red ones for the reference building. We heard about the assessment system for sustainable buildings in Germany. It's a B&B system. I don't have to explain it here. We have the 5 categories: ecological quality, economical quality, social, cultural, and functional quality, technical quality, and process quality. And for the school building, a pre-assessment has been done. And here you can see the values for all these categories. I don't step into detail. And the result is that the Plus Energy School will reach the gold medal, hopefully. It's right on the border between silver and gold. The German standard building is there, it's a bronze status, and the required standard quality for federal buildings in Germany is here for the silver category. So it's a quite good building, and if we compare it with the LEED or with the BREEAM, the other systems, you can see the value where the building will be. Okay, I think it's, finally I would want to say that I think it is possible to realize a sustainable, good building with attractive costs. And if you look at the life cycle cost, and I said it's more than 20% cheaper than a traditional normal building, so that could make hope to realize more of these projects. Thank you very much.